Welcome back. In this second part, we will see how to detect an earthquake and how to observe a tsunami. So, what is an earthquake? As I had mentioned in the first part, the earthquakes occurs on the plate boundaries. So, when an earthquake happens, the block, uh, the two blocks from both the plates, one of them moves up or down. So, when an earthquake occurs, the block which slides against the other, it slides on a plane. So that plane is called the fault plane. And where the earthquake occurs, deep down in the earth or below the ocean floor, that's called the hypocenter. And the point which is, if you project up on the surface, that is called the epicenter. Those, the surface where they slip is called the fault or fault plane. The location below the Earth's surface where the earthquake starts is called the hypocenter, and the location directly above it on the surface of the Earth is called the epicenter. So, before or after a earthquake, there could be several major or minor earthquakes, what we call foreshocks, if those earthquakes are happening before the main earthquake, or the earthquakes are happening after that earthquake, are called aftershocks. So, what causes the earthquakes and where do they happen? Why the earthquake should happen at all on our Earth? As you see that from this picture, this cone, it shows a cone which is cut on the Earth, which shows that our Earth is made of a core, or it has a inner core and outer core, and there is a mantle, and above that the lithosphere or the hard surface. So, except that very thin layer of about 80 kilometers or so, the entire Earth, our interior of the Earth, it is still in the molten stage, which consists of the core and the mantle, and on this molten sphere, our lithosphere is there. So, that thin lithosphere, which is about 80 kilometers, whereas the core is about 3,500 kilometers, and the mantle is about 2,800 kilometers, and on top of that, the thin layer of 800 kilometer, that's the top of the some portion of the top of the mantle, and the lithosphere, that is floating on this molten mantle. So, and it is broken in pieces, like it is shown in this picture here, in different plates. So, these pieces keep moving slowly against each other and sliding past one another and pushing into each other, and we call these pieces tectonic plates, and edges of the plates are called the plate boundaries. And as I explained in the first part, they can break at any time as a strike slip, or moving parallel to each other, or sliding one portion below the other, or sliding up. So those are the three ways the plate can break. So when a plate breaks, it releases the energy. The energy is released in the forms of waves, and these are called seismic waves. And there are mainly four types of waves are created when an earthquake occurs. And one and first and foremost, the wave is called a P wave, and these waves are compression waves in nature. They move back and forth, back and forth. So they travel at a very high speed, and they are the fastest waves, and their speed is the highest among all these four waves. And they have compression waves, or like a spring. If you pull and leave it, how it moves, these waves are traveling. The second type of waves are called the secondary waves, or the S waves. They are like transverse waves. If you take a rope and just move it up and down, you see that how the wave is created on that rope. That's the way they move. and the other two waves, which are called the love waves or the Rayleigh wave, these are surface waves, whereas the other two are entire or affect the entire body of the earth. From the epicenter, they just radiate on the entire body of the earth, and when they reach, they create this love waves and Rayleigh waves. And the love waves has the property that they shake on the sideways. So all these three motions, one is the compression motion, other one is the normal wave motion by the secondary waves or the S waves, and the love waves, they create the motion on the sideways, and that is why we get large shakes when an earthquake occurs. Our entire building, our houses, everything gets is shaken because of this energy is passing through the earth at that particular time. So, how do we measure or record the earthquakes? As I mentioned, the earthquake generates these waves and the shaking of the ground. So, the ground shakes because of the P waves, the S waves, and the love waves and the Rayleigh waves. So, all these waves shakes the ground, and if you keep a rotating drum and some pen on a heavy weight, you can record this motion, because if you keep that rotating drum fixed on the ground and the heavy weight attached with a pen on a spring or absorbing something which can absorb those motions, or a steady mechanism, the drum will just move back and forth because of the earthquake, and draw the wave pattern. So when an earthquake causes the ground to shake, the base of the seismograph, this instrument is called seismometer, and the pattern which it draws is called a seismograph, that shakes, and the hanging weight, because it is hanged on a spring, it does not shake. So it draws that pattern on this on that drum. For example, you can see a sample seismograph, and the wiggles which it happens, it depends on how vigorous the earth, or what is the magnitude of the earthquake, or how vigorous the earth has shaken. So the size of the earthquake depends on the size of the fault and amount of slip on the fault, and faults are many kilometers deep beneath the earth's surface. So the seismogram recordings made on the seismographs at the surface of the earth are used to determine the size or magnitude of the earthquake. A short wiggly line that doesn't wiggle very much means a small earthquake, and a long wiggly line that wiggles a lot means a large earthquake. So, from the length of the wiggle, we can find out what is the magnitude of the earthquake. So, seismograms are also used for locating the earthquake. As I mentioned earlier, the P waves travels much faster than the S waves, and the seismograms records both the waves. So if you take the time difference between P and S wave, like when a lightning occurs, first you will see the lightning, and then little later you will hear the thunder sound. So if the lightning is occurring very near, both are happening at the both you will hear at the same time. So by taking the time difference between P and S waves, we can calculate the distance where the earthquake has occurred, and if you take that distance and draw a circle with that distance as the radius, you will find that the earthquake has occurred somewhere on that circle. Similarly, if you take from another station, another seismogram, and also again determine that distance, you can draw another circle. So you need a minimum 3 seismograms to determine where the earthquake has occurred. So from the wiggle amplitude, you can find the magnitude, and by drawing these 3 circles around the 3 stations, you can determine where all the 3 circles intersect. That is the point where the earthquake has occurred. So this is the method, or what is called triangulation method, is used to determine where the earthquake has occurred. So how to express this magnitude? That was bothering the scientists for quite long time. How you can say that this is a 10 magnitude or 5 magnitude? So in 1935, Charles Richter, he defined a scale popularly known as Richter scale. That is what popularly we all know that. But that has several drawbacks, and in 1970s, another scale was defined called moment magnitude. And for the earthquakes, if they are adequately measured, then the Richter scale as well as the moment magnitude, the numbers will be same, but these are two different scales. So it is defined as in logarithmic scale, and because they are defined as the logarithmic scale, one magnitude increase in the Richter scale represents a tenfold increase in measured amplitude. In terms of energy, each whole number increase corresponds to an increase of about 31.6 times, and the amount of times the energy released, and each increase of zero point 0.2 corresponds to approximately doubling of the energy release. So when we talk about 7.4 magnitude and 8.9 magnitude, the energy content is much higher, and you can imagine what kind of energy must have been released due to the 9.1 magnitude earthquake in 2004. So how we will observe these tsunamis? To observe the tsunamis, there are the modern instruments called tsunami buoys, which are positioned in the ocean, which consists of a tsunami bottom pressure recorder, which is fixed on the ocean floor, that records the changes in the water column as the tsunami wave moves above that, and then that communicates using the acoustic telemetry with the surface buoy, and the surface buoy has a satellite communication system. So these are called tsunami buoys, and if they are positioned in the ocean as the tsunami wave passes through, they will record that data, and via satellite we can get that information at the warning center. Of course, there are tsunami buoys deployed by India in the Indian Ocean, and we will look at that in more detail in the next session when we discuss about the warning process. And this is a typical record from the tsunami buoy. You can see that when a tsunami occurs, the wiggle like signal is generated, and that keeps on continuing as the wave passes over that. Else, that will be just rise and fall due to the tides on that record. The other type of instruments that we can use are called coastal sea level gauges, or they are also called tide gauges, because mostly they are used to observe the tides or record the tides at the harbors, and they are located on the coast. So if you get the data from far away tide gauge, you can get to know that if the tsunami wave has approached there, and then use that for the warning purposes. So the old tide gauges were sort of a float which is moving up and down in a well at the port, and that is connected with a pen and a chart drive, and the new ones are replaced with acoustic technology or the radar technology. So these are some of the examples of this radar tide gauge. A small radar is looking down at the sea surface and records the changes in the sea level. Similarly, this is a float, and that float will move up and down as the water level changes, and that gets recorded on the chart which is fitted with that. So there are different types of tide gauges, and this picture shows the tide gauges which are available all along the Indian coast as well as in the Andaman Nicobar islands. And these are the major two observing systems which are used to detect the tsunamis. With this, we conclude the second part on observing the tsunamis and detecting the earthquakes. And the third part, we will look at how to model the tsunamis, because modeling the tsunamis is very important for the prediction of tsunamis.